Hello everyone. In today's lecture, we will continue our discussion of the pulse modulation. In the previous lecture, we've learned that there are two types of pulse modulation, analog pulse modulation and digital pulse modulation. And we've seen that both types require that the message m of t is first sampled, and then the resulting samples m of nts are used in the modulation process. That's why the previous lecture was completely dedicated to the discussion of the sampling process, its mathematical description, and the implication of the sampling process on the frequency domain. In today's lecture, the first topic at hand is the pulse amplitude modulation, or PAM. PAM is the simplest and most basic form of analog pulse modulation. In PAM, the amplitude of regularly spaced pulses are varied in proportion to the corresponding sample values of a continuous message. In other words, if you remember from the previous lecture, we have train of pulses acting as our carrier, and we choose one characteristic of this train of pulses to change in accordance with the message. This characteristic could be the amplitude. In this case, we will get what's called pulse amplitude modulation. Or we can change the position of the pulse in accordance with the message. In this case, it's called pulse position modulation. Or we can change the width of the pulse in accordance with the message. It's called pulse width modulation. So pulse amplitude modulation basically changes the amplitude of the pulses we have in accordance with the sample values of the message we have. Of course, the pulses can be of a rectangular shape or any other appropriate shape, and the pulse shape determines or affects the bandwidth required for transmitting the PAM signal. This definition of the pulse amplitude modulation is similar to what's called natural sampling. So, what is natural sampling? So, in order to understand what is natural sampling, let's first start talking about what is instantaneous sampling. As we have seen in the previous lecture, in instantaneous sampling, we multiply the message m of t with a train of impulses, and these impulses are located at 0, ts, 2ts, 3ts, and so on. So, multiplying the impulse with the function m of t, we will get the sample or the value of the message m of t at instant 0, and then again at instant ts, and at instant 2ts, and so on. That's why this is called instantaneous sampling. We are retrieving or having the message value at one instant. But in natural sampling, instead of multiplying the message with a train of impulses, we multiply the message with a train of pulses, which I'm going to draw it now in green. So as you can see now, we are multiplying the message with a pulse, not an impulse. So the impulse would have a width of 0, ideally, but a pulse would have a finite width. And as you can see over here, the top part of the pulse is taking the shape of the message m of t. This is called natural sampling. So if we carry on, now we have this sample as well, and a pulse instead of an impulse. And as you can see, the top part of the pulse is taking the shape of the message. This is what's called the natural sampling. Okay, so this is natural sampling, and how it's related to the instantaneous sampling we have seen in the previous lecture. Going back here, it says that the pulse amplitude modulation we have defined is somehow similar to natural sampling, but where the message signal is multiplied by a periodic train of rectangular pulses. So as we can see over here, the message m of t is multiplied by rectangular pulses instead of impulses. In natural sampling, however, the top of each modulated rectangular pulse is permitted to vary with the message signal, whereas in PAM it's maintained flat, and this is a very important difference. So in natural sampling, the top part of the pulse is taking the shape of the message. It's allowed to change with the message. As you can see here, the top part of the pulse is allowed to change with the message. But in pulse amplitude modulation, actually, which I'm going to draw right now in red, the top part of the pulse is kept flat. So instead of allowing the top part of the pulse to change with the message, it's kept flat. So we take, as if we take the instantaneous sample and hold its value for the entire duration of the pulse. So again, we take the instantaneous sample at 2ts here and keep or hold the value for the whole duration of the pulse. This is the pulse amplitude modulation. So as we can see, pulse amplitude modulation and natural sampling are similar in that instead of using an impulse, we use a rectangular pulse, but the difference is that in the natural sampling, which is shown here in the green curve, the amplitude of the pulse changes with the message, or is allowed to change with the message, whereas in the pulse amplitude modulation, the top part of the pulse is fixed at the sample value at 0 and at TS and at 2TS. So going back here, so in natural sampling, however, the top of each modulated rectangular pulse is permitted to vary with the message, whereas in the PAM it's maintained flat. As we can see in this figure, so the dotted curve here is the message m of t, and again we're taking the sample value at instant here at instant 0 and keeping it flat for the duration of the pulse. Here at ts we're taking the sample at ts and keeping it flat, holding it for the duration of the pulse, and so on. This is the pulse amplitude modulation, the PAM signal. M of t is the message, the dotted line or the dashed line, and S of t, this one, is the corresponding PAM signal. And here we have two symbols we need to take good care of. TS is a sampling interval. It's the separation in time between two consecutive samples. Whereas capital T over here is the pulse width. As we're going to see, the pulse width will have a great effect on the bandwidth required for transmitting the PAM signal, as well as it will affect the recovery of the message, as we're going to see later on. So, to wrap things up here, the two operations involved in the generation of PAM signal are: first step is to perform the instantaneous sampling of the message. Every TS, or using a frequency Fs, sampling frequency Fs, such that Fs satisfies Nyquist condition, that is Fs larger than double the bandwidth of the message, in order to avoid the aliasing distortion. And then, after we do the instantaneous sampling, we lengthen or extend or hold the value of the sample for the entire duration of the rectangular pulse. So let me go back to the whiteboard over here and try to draw a curve that would help us to understand this. So basically what we are saying is that if this is the message m of t, we will start by taking instantaneous samples, and then we will extend or hold this value for the entire duration of the pulse. And here we will take instantaneous sample, and then we will hold or keep or lengthen the duration of the rectangular pulse here, and so on. Instantaneous sampling, holding the value, and so on. That's why the kind of circuit that performs this operation is called sample and hold, because you will sample the signal and hold the value until until capital T, from 0 to capital T. You will sample the signal, hold the value for the entire duration of the pulse. That's why it's called sample and hold. So in digital circuits, the circuits used to perform such an operation is called sample and hold, and hopefully in other courses you will learn about these circuits and how do they operate. So, why do we lengthen or extend the duration of the pulse? Why do we extend the duration of the pulse? It's basically to avoid the use of excessive bandwidth, to reduce the bandwidth. But how does the bandwidth change with the duration of the pulse? What is the relation between the pulse duration and the bandwidth? In order to answer this question, let me move to our whiteboard and see how it goes. So in order to understand the relation between the pulse width T and the bandwidth, let's consider a rectangular pulse centered around 0, and the width of the pulse is capital T and amplitude A. Using Fourier transform, we know that the spectrum of this rectangular pulse is a sinc function whose amplitude is AT, and the zero crossing of the sinc function is located as 1 over T, 2 over T, and so on. So let's say that the bandwidth of such a signal would lie between these two zero crossing, as they include most of the power. So if we say that the bandwidth is related to the zero crossing here and there, this is the bandwidth. This means that the bandwidth is proportional to 1 over T, which means that as capital T increases, as the pulse width increases, the bandwidth will decrease, and the other way around. If the pulse width is reduced, the bandwidth will increase. So they are inversely proportional. So going back here, we can read this statement one more time. One important reason for intentionally lengthening or increasing the duration of each sample is to avoid the excessive channel bandwidth, since the channel bandwidth is inversely proportional to the pulse duration, as we have seen over here. Increasing the pulse duration will reduce the bandwidth requirement. However, there are other restrictions on the duration capital T, as we are going to see later on from our analysis. Okay, so now let's start doing some mathematical analysis of the PAM as we have defined it. Here we're talking about what's called sample and hold. As we have defined the PAM, we do instantaneous sampling, and then we hold the value for the entire duration of the pulse, which is capital T. So let's try to analyze this kind of signal and see the bandwidth requirement and what kind of problems we should expect when using this kind of modulation. So the signal, the PAM signal defined so far, can be mathematically described as follows. S of t equals summation over a variable n from minus infinity to positive infinity, m of nts times h of t minus nts. So what's m of nts? It is the sample values of the message m of t, taking an instance nts. So when n is 0, it's m of 0, m of ts, m of 2ts. It's the samples of m of t at instance nts, multiplied by a function h of t. What's h of t? It's a pulse shape. The rectangular pulse we have been using so far, we will call it h of t, But this rectangular pulse is shifted in time as well. Instead of having h of t, it's h of t minus nts. So if we put n equals 0, we'll be having m of 0 times h of t, which is the pulse, rectangular pulse we have at the origin at t equals 0, times the sample value at time instant 0. And then if you put n equals 1, we will have m of ts multiplied by h of t minus ts, which means that we will be shifting the rectangular pulse we have from 0 to time instant ts, and then the amplitude of such pulse would be m of ts, which is a sample value, and so on and so forth for all values of m of nts. So ts is a sampling interval, m of nts is a sample value of m of t obtained at time instant t equals nts. So in order to understand this equation, let's move to our whiteboard over here, and as you can see, this is h of t, this is the pulse shape we have, and these are the sample values of the message m of t. So the equation is simply saying that h of t will be shifted at 0 and multiplied by the amplitude or the sample value at 0. And then we will shift h of t at instant ts and give it an amplitude equal to the sample value here. And then we will shift it again at 2ts and give it the amplitude or the value of the sample over here, and so on. So let's try to do this and see how it goes. So we will shift h of t at 0 like this, and the amplitude will be equal to the sample value. And then we will shift it at ts and the amplitude equal to the sample value. Shift it at 2ts, then shift it at 3ts. As you can see, shifting the pulse h of t we have here, we give it the amplitude of the sample at the same instant. And so we can write the equation as follows. We have the pulse h shifted at instant nts and multiplied by the corresponding sample value m of nts. And then you add all these together from minus infinity to infinity. This will give you your PAM signal s of t. This is the equation we have over here. S of t equals summation m of nts times h of t minus nts. So h of t, as we have said, is a standard rectangular pulse. It's basically a pulse starting from 0 to capital T with a value of 1 and 0 otherwise. And as you can see here, this pulse is kind of shifted in time. Instead of being centered around 0 as we have been doing in the Fourier transform chapter in our course, now this pulse is kind of shifted to the right, and the shift is t by 2. That's why it's rect t minus t by 2 over capital T. This t by 2 is the shift to the right. So the spectrum of such a signal is a sinc function. As we know, rect function in the time domain will give us sinc function in frequency domain. And in front of a sinc over here, we get the area of the rectangular pulse, which is capital T. It has the height of 1 width of capital T, so the area is capital T. Sinc F times the width of the pulse, which is capital T. And now because this rectangular pulse shifted in time to the right, we multiply by e to the negative j 2 pi f t over 2, which is the shift. That's why we get e to the negative j pi f t. And as you can see over here, we have a phase shift, and due to the delay we have in time domain. So usually the shift in time domain will give us some sort of a phase shift in frequency domain. And as we can see here, this is a rectangular pulse we have from 0 to capital T. It's not centered around 0, it's shifted to the right, and this is the corresponding spectrum. And as you can see, the spectrum of this rectangular pulse is a sinc function, as a 0 crossing is 1 over t, 2 over t. So if we consider this to be the bandwidth from minus 1 over t to plus 1 over t, you can see that the bandwidth is inversely proportional to the width of the pulse. So a wider pulse will give us a smaller bandwidth and vice versa. Okay, the previous expression of S of t can be seen as a convolution of m delta of t with h of t. What's h of t? It's a pulse shape. What's m delta of t? It is a sampled version of m of t. The sampled version of m of t. So how's that? So if you remember from the previous lectures, by the definition of instantaneous sampling, m delta of t equals m of nts times delta of t minus nts under the summation from minus infinity to plus infinity. This basically was multiplying m of t with a train of impulses, and then after you multiply the function with an impulse, you only get the value of the function at the instant where the impulse happens. So you will get, instead of m of t, you will get m of nts. And we have discussed this in details in the previous lecture. So if we do the convolution between m delta of t, which is a sampled version of the signal m of t, with the pulse shape, let's see what we are going to get. So in convolution, we choose one signal, keep it as is, and the other one we do a mirror and shift. So I've chosen m delta of t to be the same, so it will be m delta of tau. Of course, we change t with tau, the dummy variable tau, and then h of t will be h of t minus tau, and we integrate with respect to tau. So basically, m delta of t can be replaced with a summation from minus infinity to positive infinity, m of nts delta of tau minus nts, then multiplied by h of t minus tau d tau. Next, we'll exchange the summation and integration. So it will be summation m of nts integration impulse times h d tau. So multiplying a function h of t minus tau times an impulse under the integration, we will get the value of the function evaluated at the instant where the impulse happens. But keep in mind, this integration is with respect to tau, so tau is a variable. So the first question, where does this impulse happen? It happens at tau equals nts. So the integration value would be the value of this function with tau, the variable we have, being replaced with nts. So it's h of t minus nts. So it's basically summation from minus infinity to positive infinity, m of nts times h of t minus nts, which is the very definition of the PAM signal we have just seen. So now we can understand that the PAM signal is basically a convolution between the sampled version of the signal, the instantaneously sampled version of the signal m delta of t, with the pulse shape h of t. So now that we have formulated the pulse amplitude modulation as a convolution between the instantaneously sampled signal m delta of t with h of t, now we can easily find the spectrum of the PAM signal using the convolution property of the Fourier transform. As we've seen before in the Fourier transform properties, linear convolution in time corresponds to multiplication in frequency domain. So if s of t equals m delta of t convolution h of t, we can simply write s of f equals m delta of f times h of f, where s of f is a spectrum of the PAM signal, m delta of f is a spectrum of the instantaneously sampled signal, which we have proved in the previous lecture that it will take this form. Summation of m of f minus kfs, it's the spectrum of the message m of t shifted in the frequency domain every fs, multiplied by h of f, which is the spectrum of the pulse shape we have. So s of f equals m delta of f times h of f, which is fs summation m of f minus kfs times h of f. Okay. So if we are using the rectangular pulse h of t, the rect function, the h of f, the spectrum will be the sinc function of this form which we have discussed a few minutes ago. So the spectrum of the PAM signal s of f would take the form this summation times this sinc function. So in order to understand this equation and the implication of having this h of f, let's move to our whiteboard over here. So here, this is the spectrum of the message m of t, m of f. And as you have seen in the instantaneous sampling, the spectrum m delta of f will take this form. It will basically be this m of f repeated at 0, and then repeated at fs, and then at 2fs and 3fs and so on, and minus fs and minus 2fs and so on. This is basically m delta of f. Okay, so using m delta of f, we understand this and we have seen this before. But here in the equation, m delta of f is multiplied by this sinc function, sinc ft. Forget for now about this phase shift. Forget about the constants t and fs. Let's consider just the sinc function, sinc ft. If you want to draw this sinc function, where is the zero crossing of this sinc function? The zero crossing of this sinc function would be at 1 over t, as we have just seen. So let's try to draw the sinc function using the red color over here. So this sinc function will be multiplied with the spectrum of m delta of f, which basically will interfere or will distort the shape of the spectrum. That's why it's not simply to put a low-pass filter in order to recover this message. Instead, we need to do something different over here to recover the message, because using a rectangular pulse instead of an impulse, by lengthening the duration of the impulse to have a width capital T, we get this sinc function, and this sinc function will distort the spectrum in a way. Okay. Moving back over here, so let's consider the task of recovering the original message m of t from the PAM signal. This is what we've been saying a few seconds ago. If we want to recover the message m of t from this signal, the PAM signal, we have two problems. The first problem is the replicated spectrum. The spectrum is being replicated every fs. And the second problem is this sinc function, which will distort the spectrum in a way. If we do not have the sinc function, we could simply have used a low-pass filter, which will choose the spectrum centered around 0 and kill all other replications of the spectrum, and then we will have recovered our signal. And this filter we have called before the reconstruction filter. And we have used it with instantaneous sampling. So the first step to recover the message m of t is to use a low-pass filter, as we have done in the instantaneous sampling in the previous lecture, which would allow m of f to pass and kill all the shifted replicas of m of f, that is m of f minus k fs. So basically, this filter will be allowing m of f to pass, centered around 0, and all the replicas at fs, 2fs, minus fs will be killed using this filter, which is called the reconstruction filter. But the output of this low-pass filter would have the spectrum m of f times h of f. It's not just m of f, it's m of f times h of f. That's why it's kind of distorted in a way, which is a distorted version of the original signal. As you can see over here, the spectrum m of f we have here is multiplied by the sinc function, this red curve. Let me emphasize this curve a little bit. So it's multiplied by this sinc function. So the spectrum is kind of distorted right now. It's kind of distorted. So first of all, this distortion is called the aperture effect. It's called the aperture effect. It consists of amplitude distortion and a time delay of t by 2. Time delay of t by 2, it happens because the pulse is kind of shifted to the right by t by 2, and the amplitude distortion is happening due to the sinc function multiplied by the spectrum. If you go back to the equation, we have a sinc function, or h of f, multiplied with the spectrum over here. So we need to use what's called an equalizer. An equalizer is a device that tries to equalize the effect happening over here. So an equalizer should be used to reverse this amplitude distortion. There is nothing we can do about the delay. It's a physical phenomenon, we cannot cancel it, but the amplitude distortion can be reversed in a way using an equalizer. Equalizer basically is a device whose frequency response has this form, 1 over h of f magnitude. So if the spectrum m of f is multiplied by h of f, we simply will add a device, it's called an equalizer, that have a frequency response 1 over h of f, which is 1 over the sinc function pi f over sine pi ft. This kind of device will reverse the effect, the aperture effect, and will get us m of f. Of course, the design of an equalizer is a challenging task, and obtaining a device with this kind of frequency response is not easy, and we're gonna talk about it later on, maybe in different courses. So now we have our reconstruction filter. So the PAM signal going through the reconstruction filter, hence killing all the replicas of m of f at fs, 2 of s minus fs, and only keeping the one replica or the original signal at 0, m of f, multiplied by h of f, and then we have an equalizer whose frequency response is 1 over h of f, will give you the message m of t. Usually the amount of equalization needed is kind of small. If t over ts is less than 0.1, the distortion is less than 0.5%, in which case we usually will not need an equalizer and we'll forget about it. That's why we have said that there is a restriction on the value of t. If t is getting larger and larger, this means that the zero crossing of the sinc function will be closer to the origin and the distortion would be larger. So we have two restrictions. You want t to be large in order to reduce the required bandwidth, but also you want it to be kind of small compared to ts in order to reduce the amplitude distortion, and maybe you can eliminate the need for an equalizer at all. So the transmission of a PAM signal imposes stringent requirement on the amplitude and phase responses of the channel due to the relatively short duration of the transmitted pulses. What is this supposed to mean? Now we're using pulses of duration capital T. This capital T has to be kind of short in order to reduce the aperture effect. And this short duration, and also in order to transmit data faster, this shorter duration actually will require larger bandwidths, and then the channel has to be of large bandwidth, which is not something that's available or we can achieve easily. So, as we are going to see later on, the PAM signal can be seen as a counterpart of AM. In AM, we have a sinusoidal carrier which changes its amplitude in accordance with the message. In PAM, we have a train of pulses which change their amplitude in accordance with the message. That's why we can roughly say that both AM and PAM offer the same order of performance, more or less. And by performance, we're talking about the bandwidth requirement and the noise behavior. That's why we're not expecting the PAM to be superior in any way to AM. As a matter of fact, the noise performance of PAM can never be better than the direct transmission of message, like sending M of T as is. And That's why PAM is mainly used to prepare the messages for what's called time division multiplexing, which we will discuss by the end of this chapter. And this statement actually applies for all kinds of analog pulse modulation. All kinds of analog pulse modulation offer the same order of performance compared to AM, FM, and PM, because we're still changing the amplitude or the position or the width, which are all analog or continuous variables in accordance with the message, and this implies the same kind of performance in terms of bandwidth and noise behavior. That's why it's very important right now to see the other type of pulse modulation, which is the digital pulse modulation. So, in digital communication in general, the amplitude of a discrete time signal is quantized, and this is the very first and very important difference between continuous pulse modulation and digital pulse modulation. In analog pulse modulation, the amplitude is still continuous. In analog pulse modulation, we have discreteness in time imposed by the sampling process, but the amplitude of the message is still continuous in the amplitude. It can take any value. But in digital communication and in digital pulse modulation, the amplitude of the discrete time signal is quantized. What is quantization? It's basically forcing the amplitude to take only discrete values. In other words, we are forcing discreteness in amplitude as well as the discreteness we already have in the time. So, in order to understand the concept of quantization and the discreteness in amplitude, which is used in digital communication, let's move to our whiteboard over here and take a look at this signal we have here. So this signal in black, this is the signal M of t we have. And as you can see, it has continuous amplitudes. Amplitudes can take any value. So the very first step is to take samples, which is to have discreteness in the time domain. So if we have a sample over here, and then we have sample here and there, all these samples are discrete in time, but yet their amplitude can take any value. The amplitude is continuous. And this is what was used in the analog pulse modulation. But right now in digital pulse modulation, we're looking for something different. This amplitude should be quantized. In other words, it should not allow to take any value. It should only be allowed to take certain values. So let's say we will allow the values here, the red levels over here. Only these red values are allowed. So let's see how it goes. So we say that if the message M of t is lying in the range between M1 and M2, all the amplitudes in this range will be represented by one value. We will call it V1. So all the amplitudes in this range between these two red levels, M1 and M2, will be represented by a value V1. And similarly, all the message values between these two levels, M2 and M3, will be represented by just one value, which is V2. This way, the amplitude of the message will not be allowed to take any value. It will only take discrete values, V1, V2, V1 here, V2 and V3 and V4 and so on. And these discrete values are the values which are going to be transmitted. So let's go back over here and read it one more time. In digital communications, the amplitude of a discrete time signals is quantized. And the quantization means the amplitude is allowed only to take discrete values In other words, we're imposing or forcing discreteness in amplitude. And we're going to talk about quantizers in a few minutes from now. So, in general, digital communications has many advantages over analog communication systems. First of all, the discreteness in amplitude results in a better performance against channel noise and signal distortion. Again, the discreteness in amplitude is a great feature actually, and it offers resilience or immunity against the channel noise and signal distortion. In order to understand this, let's use this example. Let's assume that we have a message that has been quantized and the amplitudes are allowed only to take two values. Let's say this is V1 and this is V2, only two values. The amplitude is quantized. And this signal is transmitted over our channel. If we have noise superimposed on this signal, the red signal over here is the noise, even though the signal is contaminated with noise, but we can clearly see that this level is still V1. And we can clearly see that this level is still V2. Even though we have this noise superimposed on the signal, we can still get the correct values of the message. This happens basically because the amplitude is discrete. We can only have two values, V1 or V2, let's say 0 volt and 5 volts. If we have 0 volts and 5 volts, having noise superimposed on the 5 volts, making it 5.5 or 4.9 or 4.7, we still can say this is 5 volts. Same for the 0. So the first advantage is basically due to the discreteness in amplitude, we can get better performance against channel noise and signal distortion. The second advantage is that having the amplitudes quantized, we will get a sequence of numbers. At the end of the day, any message right now will be a sequence of numbers, discreteness in time and discreteness in amplitude. Any message will be a sequence of numbers. Being a sequence of numbers, we can use a so-called error control coding in order to detect and correct errors. Error control coding is basically some sort of mathematical operation that can be performed on the message, the sequence of numbers we have, and then we can use it to detect and correct some errors. And in order to understand this, let's move to our whiteboard over here, and let's say we will have an example. Let's say the simplest form of error control coding would go like this. Let's say we have a word of 8 bits we are going to transmit, and let's say we will agree that we will keep the last bit as a flag we are going to use, and it will not carry any data. So let's say we will agree that you will send always even number of ones. Even number of ones. So let's say the data goes like this: 1 0 1 1 0 0 0. So now we have 1 2 3. We have 3 ones, but we've agreed that we should be transmitting even number of ones. So I will be adding 1 over here. This one is called the parity bit. And this parity bit will be used by the receiver for error detection. How's that? Let's say after transmitting this message through a channel, this one, due to noise, will turn into 0. So now the receiver will be counting the number of ones, 1, 2, 3, and it will say, okay, we've agreed on transmitting even number of ones. So the receiver will be able to detect that there's some sort of error. So here we're talking about error detection. More advanced algorithms can be used for error correction. So one advantage, the second advantage of digital communication is that we can use what's called error control coding. It's kind of mathematical operation that will be performed on the message before transmission, and then at the receiver it will be repeated again, and the two results will be compared. If they're the same, more or less, then we will have the same message and no errors. But if they are different, we can detect that we have an error, and then we can say we can detect and sometimes correct the error. The third advantage is the possibility of using encryption. Again, because we have sequence of numbers, we can use encryption techniques, which again sort of mathematical operations performed on the message in order to encrypt its content, to improve security. All these advantages were not even possible to think of for analog communication. Also, digital communication is more efficient in terms of bandwidth and SNR, and you're going to see this maybe later on in another course. And also, being a sequence of number, we can integrate the audio and video signal with computer data. Computer data by nature is 1 and 0, is digital. So by digitizing or transforming the audio and video signal into discrete time signal and then quantizing the amplitude, we can transform them into ones and zeros, binary data, and can be integrated with computer data. And also for long distance communication, regenerative repeaters can be used to prevent the accumulation of noise and distortion. Basically, regenerative repeaters use the fact that the binary, the data we have is resilient against noise. So even if we have some noise, we can reject it. And even if we get any errors, we can use error control coding to correct some of these errors. This is basically what's called the regenerative repeaters. All these advantages, of course, come at the expense of increased system complexity. So, in the next part of today's lecture, we actually will start talking in more details about the quantization process, which is the step that would complete the transition from analog to digital communications.